Hello everyone, it's Calder from 19. Today is 93 in my challenge day. And in the last video, I applied the boilerplate given by the MB Pro core library. And I tried to resolve the issues and I figure out everything that I faced in the compile time. So if I run my application right now, I can see that this unmaterial corner box inside my scene can is rotate it. And the basic lighting just implemented itself by the boilerplate because they give some vertex shader and default fragment shader for uh, uh, simple scenes. So I can change the light positions and intensity by modifying the slider in the I'm GUI. Okay, so everything works fine. Now, finally, I'm going to write some rendering algorithms in my application. And what I'm going to do today is I want to bind the HLSL shader language in my application because the HLSL format is supported by Microsoft, and I'm using the Visual Studio as my IDE. And the good thing is, one of the good thing about using the HLSL because the format is supported by in the IDE, so it can coloring the text or the syntax word, so I can easily can figure out where which part is wrong when I wrote some wrong code. Also, it catches some the syntax error at the IDE layer. So it's really good thing to apply the HLSR binding before I start to write many rendering algorithms further. So, okay, let's start. And before start to making a binding from HLSR to SPIR-V, let's figure out what is the structure of the boilerplate code first, so that I can modify any part that I want to modify. So first, um, we set a GLFW error callback inside the main CPP. And first of all, this main CPP is a front end of this application, uh, which is define some object models and scene setting up scene components inside this front end, like the resolutions and IMGUI layer, also the applications level. Show you. And this SPIR's app is a backend of this application. So it implements some Vulkan API abstractions um, inherited by the app-based VK abstract class. So here are some bunch of the override function as a virtual function in the parent class. So some of the abstractions to create some models and create the descriptor layout and pipeline. So maybe later I can apply the DirectX backend by keeping up this structure, so that I can just uh, freely change the backend part while keeping the front end part here as a constant. So to start Vulkan app, we need first this MVVK context create info. This manages some instance extraction or the device extension given by the Vulkan API so that we can manage the extensions and the context of the application easily by using this create info. So if we want to add some extensions and the device, some of the extension that we want, we just need to call this add instance extension or the device extension based on the type of extensions and the extension name macro. So we added some swap chain extension name, swap chain extension for device, and the debug utils, which is a Vulkan validation layer in the instance extension. Then we create actual BK context struct, and we call the init instance to initialize these contexts. And this context provides device casting. So maybe there a function requires the context. So okay, first.h. Here m device. So let me show you what is the m device in the header file. So m device is nope. I think this defined in the app-based VK. Let's go to definition. Nice. Yeah, as you can see here, we have a VK device M device, which a VK device field with the name of M device, and H. And we pass the VK device reference when we call the setup function of this virus app. And if we go to the main CPP, you can see the VKCTX has M device field, which is the VK device type. So we can set up with this context so easily. And this init device means create a logical device for the physical device. And simply the logical device uh, is a role of the abstraction between the physical device and the logical device. So we don't directly access in the physical device in the Vulkan API. So we need to use the logical device, which is the VK device type. If we want to, when we want to access in the physical device functions, then we can access in the logical device first. And additional information for the swap chain presentation for the to present our image in the window. The window means that like this program in our Visual Studio, we are seeing the window with the GUIs with a bunch of GUIs. In this case, we need a surface. Surface is as I know, as my previous knowledge is a interface of the display. So we uh, so we stack the colors into the swap chain images, and we can transfer the swap chain image to the surface. The surface takes the drawing logics instead of accessing the display directly. So we create the surface first, and we set GCT which is the graphics compute transfer queue at once. And we need to set up the viewers app and create swap chain function, depth buffer, and the render pass, and frame buffers. This is a basic operations order of operations when we want to represent an image in a swap chain. I guess they hide a lot of logics in these functions, but if I have time, I'm going to analyze these functions, how they implement these set of functions later. And then we init the GUI, we load model, and the off-screen render. In this application structure, they are using the off-screen render and the post-process pipeline, which means that mm, we don't we don't draw the image directly in the surface because some of the rendering algorithms require some buffering on the image. So maybe it is really useful to buffer image first, and then we draw image, relate this image to the swaption's display surface later, so that we can set up some rendering algorithms between the this presentation on the surface and the buffering images. We can place some rendering algorithm between of them. For example, ray tracing pipeline requires it, and the G buffer, which is used in the deferred shading, also requires the buffering on the image. So that's why we are using off-screen render in this application. And obviously, we need to create a descriptor cell layout in the graphics pipeline. We are using the rasterization techniques. And we need to set a uniform buffer for camera manipulation. And this obj description buffer is for the indices and the vertices and shapes, normal vectors of the vertices, and texture coordinate of the obj model. So in the corner box obj model, they have some bunch of information of the vertex, each vertex. Then we just simply create obj description buffer here. And then we create the post descriptor and post pipeline. Let me see. I'm curious that which post pipeline is used here. Yeah, it is also the graphics pipeline pipeline, but graphics pipeline generator combine. I know that. It seems that the post graphics pipeline is not the initial pipeline in the application, so it requires some context of the application before it draws something on the screen. So it requires a render pass, which is only the concept exists in the Vulkan API. Let's get back to the main CPP. And finally, we set up the GLFW callbacks with the window by passing the window pointer and the I'm GUI import GLFW init for vulkan. this function is already implemented in the imgui imgui project. Yeah. Finally, we set up the main loop. Until the glfw window should close function code, we we are looping this while we are looping these function set of operations for every frame. So first we call the glfw port events to get events from users like the mouse click, uh, some keyboard events. So we need to call these port events first. I don't know what is this. glfw new frame, because we want to draw also the UI layer as the overlay of the our render scene. It shows UI and the prepare frame. I think this frame has some get the frame buffers and swap chain acquire the next swap chain images with some the exception handling. Okay. And then we got the current frame of the frame buffers and this comment buffer mapped to this frame because we want to render images as a in-flight approaches, so that we can what we because we want to remove the vsync in the display, like the tearing issues when we saw some graphics application. And with the begin info, and we start recording comment buffer. And we first update uniform buffer. We set the clear value for the screen, and we set up the off-screen render pass. The values, view set, frame buffer, skip size. And the second, we render the tone mapper, which is a UI. No, tone mapper and the UI. This is a post pipeline. So we get render pass, get frame buffers, draw posts with the CM above, and we wait the device until it finishes every operation in the graphics processing unit, which is graphics card in our laptop or PC desktop computer. And the destroy resources and the destroy. No, this is out of loop. Yeah, maybe why are we running this application? Uh, Although we uh, get out of this the main loop, but maybe the device is used in some other parts or in the graphical processing unit. So we need to wait the device become idle state first to avoid some exceptions, unexpected exceptions in our application. And we destroy every resources, and this is the overridden function from the VK base. Destroy, the destroy window, terminate, and return the program. Okay, this is some overview of this boilerplate given by the MVP samples. Now let's find HLSL script language, HLSL shadow language in our application. Let's create a new file. the name of I don't know the convention of naming for the name the HLSL file, HLSL file extension convention. So it's just using HLSL format. So we just need to vert shader HLSL. Let's open it the open it up the PowerShell. Cmake. Okay, there was no problem in the generating our application again. Reload or then I can see the shader sources. Where is it? Where's my HLSL? Maybe it failed to load the Cmakelist, so I need to add first. Let me check first there if there is some compile HLSL directory macro in the MVPro samples, MVPro core library. Let's get into Cmake build and heroes have the Cmake core with the third party. This is Cmake. No. Set up the Cmake. Where is the Cmake? Cmake. Utilities. Compile HLSL. Unfortunately, there is no uh, macro compile macro for the HLSL, so I need to write it myself. Okay, doesn't matter. Let's create a new function in my Cmakelist. Make a pilot. So below this line, the name will be function to compile HLSL. SPIR-V. Then will be function compile HLSL directory. Set Target source test. Test. um, Target. It header dependency reflects. Set multi-value arcs to make parse arguments. To make parse arguments. Compile. Just arcs. First find the DXT program. File globe HLSL source files. File source. think it's better to set a one-line function, not directory. So SPIR-V. So to SPIR-V. Yeah, let me write down these functions. That's for let's delete the vulkan targets from here. Return. Black Lake Territory, compound test. Then we go to for each source. HLSL source. The name is HLS source from for each of the compile source. I don't need to header files yet. I think it's okay. If compile indices, let me just read as a to do now. Let's see. Let's create a compile command. Compile cmd. These compile blanks. flags. Uh, HLSL out. Name is file destination. File name. Need to list SPIR-Vs. HLSL out. We have HLSL. Okay. Yeah. This is for the compile commands for each HLSL file, source file, unless append and this new file output for here. Its name is HLSL. Please compile command GLSL out. No GLSL. GLSL out. Source. Oh, GLSL out. So because I want to this function make static for compiling HLS to SPIR-V, let's add flags here, the SPIR-V. And the list of pan GLS source. Let's create a custom command here. For the last preview. What is preview? What is preview? Special target that represent a build step that should be executed before any other extension build steps. Okay. So by setting up the pre-build, by adding the pre-build flags, we can run these run before compilation mission source. Output is HLSL out. Command. Okay, cool. exe file cmd. See. Choose source. Has there any jealous dependency? I don't have any dependency yet, so custom command. Sources. Uh, sort file. Scope. Okay, this is a function to compile HLSL source to SPIR-V. Let's test it. We might, we might my HLSL. I don't have it yet. See some end of need to call this here. HLSL SPIR. Trace. try to build this game. Um, there was an error. So I'm going to I'm going to restore this CMake generation error after finishing this recording. So today I try to make some build command function for in the Cmakelist file to compile HLSL source to and the SPIR-V. Also, at the beginning of the beginning of this video, I overviewed some the structures of the boilerplate of my application. So that's what that is basically what I did today. Uh, So, always, thanks for watching, and see you next video. Bye bye.